before class got canceled Wednesday, I wanted to teach you guys something called the Arrhenius equation. So it relates a rate constant, lowercase k, okay, at some temperature T, and you change the temperature, that reaction will have a new rate constant. Okay, remember, what is rate constant? Okay, let's just say a reaction A goes to B. It will have a rate, which is how fast, equal to this rate constant times the concentration of A raised to the power of the decay, order of decay. So before we left, we solved a rate law problem. This is called rate law. We found whether it decays with zero, first or second order kinetics. That's the exponent. And this K is something we also found. It depends on the type of reactions. Not all reactions are A goes to B. Okay, you may have some that goes A, B, C goes to D, E, F. So how fast this reaction proceeds is based upon its rate constant and the order of decay of each of these individual reactants. Right. But this rate constant, lowercase k, is quoted at a specific temperature. So this Arrhenius equation is this. I'll give you this on the exam, so you do not have to memorize it. Okay, it's going to be the natural log of rate constant K1 at some temperature T1 divided by K2 equals EA. Okay, EA is called the activation energy. It's the hump. Okay, it's the hump that the reaction has to go through in order for it to go and settle down into products. So this is like an energetic hump. So we're going to call this the activation energy. Okay, R is a constant that I'll give you also on the exam. It's 8.314 joules divided by mole Kelvin. Alright, so this times 1 over T2 minus 1 over T1. Right? So this is the equation that we will use to solve this problem. Right? Actually, this is called the Arrhenius equation. Right? Right. So don't memorize it. Just plug and play for the test. All right, so the rate constant of a reaction is 0.0047 inverse seconds. We'll call that K1 at T1. We quote it at a specific temperature. And the activation energy is 33.6 kilojoules per mole. What is this K? We'll call it K2 at this new temperature, T2. All right, so the first thing I'd like for you guys to do is, number one, convert this to joules over mole, because your constant is joules over mole. Okay, to do that, we'll multiply it by 1,000. So a lot of students didn't do this on the exam with the vapor pressure problem. They just put 33.6 or whatever. Actually, it's 33,600 joules per mole. Okay, we do that to get the units to cancel. All right, second, you see the units of R, which will be given on the test. Okay, so it's joules over mole Kelvin. These temperatures are in degrees C, so the next step would be to convert it to Kelvin. So how do you convert to Kelvin? Yeah, we'll add 273. So what's 273 plus 25? Okay, that's 298 Kelvin. What's T275 degrees plus 273? .348 Kelvin. So we have T2, we have T1, we have K1, which is 0.0047, we have K2, which is what we want to find, K2. So this is relating K at some temperature. So let's plug everything in. Natural log of K1 is 0.0047 inverse seconds. Okay, I'm not going to put units inside the natural log. Okay, K2 is what we're trying to solve for. EA is, remember, put it in joules per mole, so it's going to be 33,600 joules per mole. Okay, R is 8.314 joules per mole Kelvin. 1 over T2 is 348 Kelvin. Minus 1 over T1 is 298 Kelvin. So now our goal is to calculate and solve for K2. So we kind of did a similar problem with vapor pressure. Actually, do you remember that equation for vapor pressure? Okay, this was on last exam. It's vapor pressure. VP1 over VP2 equals delta H vaporization divided by R 1 over T2 minus 1 over T1. Okay, so that was on test 1. This is vapor pressure. This is rate constant K, both quoted at a specific temperature. Alright, so we'll do this together now. 1 over 348. Okay, minus parentheses 1 over 298. Okay, this fraction minus this fraction is this number. Take that number multiplied by 33,600 times 33,600. Okay, and divided by 8.314. Okay, I'm getting minus 1.9485, so I am going to put some extra digits in there. Either way, the units all cancel out. This joules, mole, Kelvin will cancel out with those Kelvin. So this whole block of math, this fraction minus this fraction multiplied by this, divided by that gives me 1.9485. I'll put some extra digit there too. So do we remember how to get rid of the natural log and solve for K2? Okay, what will we do? Yes, we will do E, which is inverse natural log. The inverse natural log, as Susanna mentioned, is E. So we're going to take the inverse natural log of both sides. Okay, the inverse natural log on your calculator is called E. So e to the power of natural log of 0.0047 divided by K2 equals e to the power of 1.94852. Okay. Right, so what is this on our calculator? Did you get 0.1424?
Oh, yeah. Sorry, I read the wrong thing.
Okay, so e to the power of that number is e to the power of minus 1.94852 is 0.14249. Or 85. Okay, what's e to the power of natural log of this number? It cancels out, so you just free it. So we're going to solve for K2 here. And how will we solve for K2? K2 is equal to 0.0047 divided by 0.142485. Okay, we have to put the units back on when we finish this problem. And what are you guys getting when you do this? If you can see that calculator, it's hard to see. All right, what are you guys getting? 0.033, let me try that again. 0.0047 divided by 0.142485, getting 0. Let's see here. I'll go with 0. I'll do it to 2 sig figs. I'll do 0.033. Okay, inverse seconds. Units. 0.033. Okay, and this is the answer. All right, so the K at 298 is 0.0047 inverse seconds. You raise the temperature and the rate constant speeds up almost 10 times as fast. 0.033 inverse seconds. So, yeah, if you increase the temperature, you increase the rate constant. So this is the Arrhenius equation. So something like this will be on the test as a computation problem. So you can just star it. Right, and this is our answer. 0.033 inverse seconds. Seconds to the minus 1. So if you need help with this problem, you can come see me during office hours or email me. We could work on it together. But this is something I'd like for you guys to know for the test. All right, any questions or comments? All right, let's do one more here. I will just set this up and then I'll let you guys solve for the math. All right, this is another alternate version of the Arrhenius equation. Okay, the rate constant of a reaction is 0.000450. Okay, inverse molar seconds. Okay, don't forget molar is moles over liter at 195 degrees C. So I'm going to call this K1. I'll call this temperature T1. And what is K2 at T2? K2 is 0.0032 inverse molar inverse seconds at T2, which is 258. Okay, what is the activation energy for this reaction? So the activation energy is EA. Activation energy is a hump. Okay, is a hump. Imagine putting a sweater on a child. Okay, it's very difficult up to a certain point where you get it, you put in a lot of energy, but once you get that sweater in, it's all downhill. Kind of the. Okay, so the activation energy is a hump. Okay, it's a hump. Before you get to products. All right, so natural log of K1 over K2 equals EA divided by R 1 over T2 minus 1 over T1. All right, so what is the activation energy? We got to solve for EA. All right, rate constant 0.00045. I'm not going to put any units in here. I'll put the units. Units do not go inside a natural log. Divided by K2 equals EA. That's what we want to solve for. R, I'll give you R. Okay, I'll give you R. It's 8.314 joules per mole Kelvin. T2, 258 plus 273 is 531. 531 Kelvin minus 195 degrees C. 468 Kelvin. Okay, K2 is 0.00320. 0.00320. Okay, so now we're going to solve for EA. Do you guys know how to do this math? All right, so let's do this first. Natural log of 0.0000450 divided by 0.00320 is this number here. Okay, let's natural log it. Getting minus 4.26424. Okay, it's just from the calculator. Take this number, take this divided by this, that number, you natural log it on the calculator. I'll do it again. 0.1234450 divided by 0.00320, and then take the natural log of it. Okay. All right, this thing is kind of messy, so let's leave the EA to the side. This is going to be 1 divided by 531. Okay, minus 1 divided by 468. Okay, that's that minus this is this minus number. Take that divided by 8.314. Divided by 8.314. Minus 0.000349. This Kelvin cancels. And then the moles in the denominator of the denominator goes to the numerator. Denominator of the denominator goes to the numerator. And then the joules that's in the denominator stays in the denominator. And then we have the EA here. So we have the EA. So this times EA divided by this is this number times EA. And now I'm going to solve for EA, activation energy. Minus 4.26424 joules divided by minus 0.00003049 moles equals EA. Okay. So I move the joules here, I move the moles there. It's kind of like cross multiplying. This over this will give me the answer in joules over mole. So minus 4.26424 divided by minus 0.1234304. 140,271 joules over a mole.
It isn't any significant figures. I got 1394. So would that be close enough, or is that
1394.
984?
What was your total answer?
4.264 divided by. Oh, you know what? I'm missing a zero. Let's see it.
That will do it. Yeah.
Okay.
Yeah. That's. So I think if you put in the right zero, Casey, the correct number of zeros, you should get the answer. You can also put on the exam 140 kilojoules per mole. Okay, both are right. So make sure you know how to do this on a calculator, especially the first part, but if you know how to do this part also, it's extra gravy, it's good. It's extra gravy. Okay. Okay, so the Arrhenius equation. Okay, the final thing I want to tell you guys about chapter 13 is just know that, let's see here. Okay, just want to tell you about a catalyst. Okay, a catalyst will not change K. Okay, this is the last part of our chapter 13. A catalyst will not change rate constant K. Okay, how will a catalyst make the reaction go faster? It will lower the activation energy. Okay. Okay, this is how it achieves the reaction going faster. So coming back to putting a sweater on a child, let's say instead of one person, you have two people, okay? Two people, so instead of one, lowers the amount of energy that we have to put to get the sweater on the child. So it lowers EA. Okay, that's what you want to know, whether it's an endothermic or exothermic reaction. Whatever it may be. Okay. Okay, a catalyst will make that activation energy lower. That's all you need to know. So in the red, in the presence of a catalyst. Okay, if anybody here is a biology major, they'll talk about enzymes. There's so many different enzymes in our body, in our cells. Enzymes are catalysts, so they make a reaction that's not going to happen in a lab, in a test tube, but you add an enzyme, the reaction just happens fast. So enzymes are catalysts that are produced by the body. So just know a catalyst, will it increase K? The reaction goes faster, so K has to increase, right? No. Okay? The K stays the same when you add a catalyst. Okay? This lowercase k rate constant stays the same when you add a catalyst. Okay? Then how does a catalyst work? Okay? It will lower the activation energy. Okay? So that's how the reaction rate goes faster. The reaction rate doesn't go faster just by messing around with K. The reaction rate goes faster by lowering the activation energy. So K stays the same. Let's So this is the end of chapter 13. And then Friday, we had another snow day, or an ice day, or whatever you want to call it. I thought Friday we would have class, to be honest with you. So I went ahead and assigned a recording on chapter 14, which is the equilibrium. So let's go ahead and look at that. So for equilibrium, I usually lecture with this thing here, a seesaw. You guys know what a seesaw is, right? So let's say this is the reactants, and let's say this is the products, okay? So in some reactions, they don't go 100%, right? So sometimes some reactions will be this way. So what will you have more of, products or reactants? If this is reactants and that's products, you'll have more products. Okay, what about this side? More reactants. Okay, what about this? Equal amounts of reactants and products. Okay, equal amounts. All right, so when a reaction is completed and it doesn't complete 100%, let's say it completes, I don't know, 50-50 or 95% or only 10%. 100% would be all the way here. Okay, all products, no reactants. So some reactions, they just don't go to full completion. They're 50% complete, or 15% complete, or 25% complete, or 85% complete. So the way we designate that is with what? What do we do to the arrows? Okay, we make the back and forth. Okay, when you see that back and forth arrow, okay, you have to automatically, like instinctually, know that this is an equilibrium reaction. Okay, equilibrium. All right, so for those of you that saw the lecture videos, okay, we talked about this being equilibrium as opposed to this, which is, you know, just going to C and D. Okay, this goes to C and D, but some A and B are left over. Okay, now how much is left over is based upon K. Okay, this is capital K, and this is the equilibrium constant. Is it rate constant? No. Okay, it's the equilibrium constant. Okay. And this equilibrium constant is equal to products over reactants, okay? Except we don't put solids and we don't put liquids, okay? So it's going to be concentration of C raised to its coefficient. So we always balance products over reactants times the concentration of D to the power of its coefficient, divided by concentration of A to the power of its coefficient, concentration of B to the power of its coefficient. So this is concentration. Okay, so solids don't have a concentrations. Okay, they have a density. They have a density, if you remember from that lab. So they don't get put in here. It can ignore it. Okay, and we don't put liquids in here. Because liquids are the solvent. Okay, so it's a solvent. Reactions happen in a solvent. So the liquid portion, if it's water or cyclohexane, it's just the medium. Okay, just like our cells have a cytoplasm. Cytoplasm is just the medium. Okay, it doesn't participate in the reaction. The chemicals inside dissolved in the cytoplasm. For all the biology majors, they are involved in the reaction. Okay, so no solids or no liquids. You do not put solids and liquids in here. Okay? You just ignore them. Ignore. Okay? Don't put them in this. So it's products over reactants. Okay? Each raised to its coefficient. This is also called law of mass action. All right, so a couple of things about equilibrium constant. First of all, it's called the equilibrium constant. Okay, not rate constant. This is not how fast. This is how much is left over when the reaction is done. Okay, have more reactants, more products, 50-50. In that case, the equilibrium constant is 1 because it's product over reactants. If your equilibrium constant is really, really large, greater than 1, then what does it favor? Remember, this is products over reactants. If it's large or greater than 1, then the equilibrium is predisposed or favors the products. Okay, so what will you have more of when the reaction is done if you have a large equilibrium constant, products or reactants? What will you have more of? You'll have more products. Okay, P here is products. Okay, if the equilibrium constant is less than 1, okay, 1 is greater than the equilibrium constant, which is products over reactants. Okay, what will we have more of? Will we have more reactants, more products, or will it be 50-50? What will we have more of? Here, the equilibrium is predisposed to the reactants. Okay, reactants. And if your K is equal to 1, obviously it's like this. If your equilibrium constant is equal to 1, neither you'll have products or favored, or neither will you have reactants favored. Okay, so it's just 1. All right, a couple of other things here. This K is quoted at a specific temperature, just like lowercase k, just like vapor pressure. So change the temperature, you change equilibrium constant K. All right. This K is unitless. Okay, unitless. So are we going to put units in K? No. Okay, we will not put units in capital K because this is, by the way, what is this called? Okay, it's called the equilibrium constant. Okay, capital K. And then the last thing that I want to say about the equilibrium constant is it's not lowercase k. Okay, lowercase k is called the rate constant. Okay, what gets put inside the equilibrium constant? Not solids, not liquids. So what are you left with? Okay, the only thing that you can put in this equilibrium constant are aqueous and gases. The only thing you can put in this equilibrium constant are aqueous solutions, that is, those dissolved in water, or gases. Now, unfortunately, for gases, we can express gases in 2 ways. What are those 2 ways? Pressure and concentration. Okay, moles over liter. All right, so for a gas, it could be pressure or concentration. For a gas. And then finally, we have a lot of subscripts. Okay, so if you see a KP, the P probably stands for pressure. Okay, P equals pressure. This is the equilibrium constant for a reaction with a lot of gases in it, expressed in terms of pressure. Okay, what would Kc be? Equilibrium constant expressed in terms of concentration. Okay, so what I'll teach you in the next chapter, which is chapter 15, or maybe I think chapter 14, water has an equilibrium constant. So here, W equals water. Okay, there's something called KSP. This is, again, chapter 16 or later on. This is called the solubility product. Okay, much later on in the chapter, so they have a lot of different subscripts. Okay, I'm not going to teach this to you, but there's something called KF, which is called complex ion formation, which I decided not to teach you. So, bless you. So there's a lot of different subscripts. Okay, so don't worry about any of these. Our focus will be these two. Okay, for now, for this chapter. Let's do some problems here. Okay, these are just some practice problems I've taken from a textbook. Some water. Alright, so let's just go ahead and calculate some of these equilibrium constants here. First of all, my question to you guys, is this reaction at equilibrium, yes or no? Yes. How do you know it's yes, Susanna?
Arrows.
Exactly correct. Okay, the arrows. Okay, the arrows are going back and forth. Okay. And then we have an equilibrium constant P in terms of pressure. Okay, this is 28.5. Okay, at this temperature, change the temperature, you change the value. Okay, notice that has no units. So that's nice for us. And the P stands for pressure. Okay, pressure. Okay, but we want it in terms of concentration. Right? Equilibrium constant in terms of concentration. So the equation to go from concentration to pressure and vice versa is this. Right, I'll give this to you on the exam, so you do not have to memorize it. Right, I'll give this on the test. Okay, so Kp is equal to Kc. Okay, this R, gas constant R times temperature T, is raised to the power of delta N. So R is, so there's no units, so I'm not going to put units. K has no units. So this R is this version of the gas constant, 0.0821. Okay, T is temperature, but we're going to put it in Kelvin. Okay, and this delta N is gases, moles of gas products minus moles of gas reactants. Change in number of moles of gas molecules. So okay, this N usually is number of moles, lowercase n, right? From gas laws, number of moles. Okay, but it's the number of moles of gas because we're trying to calculate the equilibrium constant in terms of pressure P. right, let's solve for this doing this example problem. Okay, and hopefully this will make better sense. It should make sense once we go over a problem, is my feeling. All right, calculate Kc for each of the following equilibrium for this equilibrium. Okay. All right, so what is Kc here? Okay, it's going to be concentration of CS2 divided by, am I going to put products over reactants? Okay, am I going to put this carbon here? Yes or no? It's an important question. Am I going to put the carbon? No. Okay, why no carbon here? It's a solid. Okay, so please don't put any solids or liquids in this. Right? Every year some student's going to put a solid in there. Okay, if you see a solid or a liquid as a state, you can ignore it. Don't put it. Solids are a density. They don't have a concentration. Okay, products over reactant. What's my other reactant? S2. Okay. Is this balanced? One carbon, one carbon. Yeah, two sulfurs, two sulfurs. Okay, so that's what this is. Okay. And then we can also do Kp, which would be pressure of CS2 divided by pressure of S2. Okay, because of gases, we can go either way. That P there stands for pressure. Usually it's in atmospheres, usually. Okay, we can express gases either as a concentration or as a pressure. All right, so this is what it is in the equilibrium constant in terms of expressing the gases in moles over liter. This is the equilibrium constant in terms of expressing the gases in terms of concentration, usually in atmospheres. Okay, they give us a number here, 28.5. There's no units, so let's put that in here. Okay, R is 0.0821. T is 500. Okay, raised to the power of delta N. So what is delta N here? Okay, how many gases do we have in the product side? How many? How many gases? Okay, what's the number in front of the CS2? 1. So 1 gas. Okay, that's the number of gases in the products minus the number of gases in the reactants. How many gases do we have here? 1. So we have 1 gas, 1 mole of gas in the product, minus 1 mole of gas in the reactant. So what is delta N? 0. Okay, so this whole thing, RT, is raised to the power of 0. Okay, so what's anything raised to the power of 0? 1. So here, when there's no change in the moles of gas, the Kc is going to equal to the Kp. Okay. All right, so we have this kink or this alteration only when you're dealing with gases. Okay, only when you have gases, you have this extra complication. So Kc is equal to Kp because there's no change in the moles of gases. There's no change in the number of moles of gases. The reaction. Okay. All right, let's look at this one here. All right, so this time we will do Kp here. Okay. Okay, we got a Kc. So what is Kc? Okay, it's a concentration, NH3. Okay, what will we raise this to? Okay, Y2,
How many moles
how many moles
there are?
there are. Okay, products over reactants divided by N2 raised to what power? 1 times concentration of H2 raised to what power? 3. Why am I raising it to the third power? Because there's 3 moles, okay? So that's expressing the equilibrium constant in terms of pressure. Here they give us the value of 0.0024, okay, at this temperature. All right, Kp is the pressure of the NH3. We'll square that, okay, because it's a gas. Pressure of N2 times pressure of H2. Okay, we have to cube it. All right, let's go back to our equation. It's asking us to calculate Kp, what is it, Kp? Okay, Kp for this. All right, I'll give you this equation for the exam. So Kp is what we're looking for here. Kc is 0.0024. R is the gas constant, 0.0821, times temperature T, which is 1,000 Kelvin. Okay, there's no units, so don't worry about it. What is delta N? Okay, what is delta N? How many gases in the product side? 2. How many gases in the reactant side? 3 plus 1, 4. Okay, so delta N is -2. Okay, so this whole thing is raised to the power of -2. So once we put this in our calculator, we'll get this equilibrium constant in terms of pressure P. Let's quickly do that before we close shop. Okay. 0.0821 times 1,000. Okay, we're going to raise it. Okay, raise it to the power of -2. That's that number times Kc, which is 0.0024. 3.5 times 10 to the, what number? 3.5, 3.6 times 10 to the -7, okay? Where do you think this reaction favors, reactants or products? 10 to the -7. Okay, it's very small, it's less than 1, so this equilibrium favors reactants. Okay, same thing here, less than 1 favors reactants. Okay, what do you think this equilibrium favors? It's greater than 1, so what will we have more of, reactants or products? This top one favors the products. It's greater than 1. All right, so this equilibrium favors the products. We'll have more products when the reaction is over and done. We'll have more reactants when the reaction is over and done. Okay, because the magnitude is less than 1 for this one. The magnitude is greater than 1 for the top one. Okay, so this is going between the equilibrium constants, pressure and concentration. We'll continue this on Wednesday, so I'll see you all. I think we'll have a lab today at 2. Try to come in at 1:45 or so, for those that want to get a head start.